Now, without going too deep into each point, I would like once again to recapitulate why the ideal filters cannot be attained. So, it has nothing to do with technology or the lack of computational power. There is something fundamentally troublesome about these ideal filters that makes them unachievable or unattainable. Let me cite these points one by one for the sake of completeness and revision from a more basic course. So, why are these ideal filters unattainable? Well, the first reason is that the ideal filters are infinitely non-causal. And this can be checked by constructing the impulse response. So, from the frequency response, we can go to the impulse response. We also know how to do that. We can go to the impulse response by taking what is called the inverse discrete time Fourier transform. So, if you have the ideal frequency response, let us call it H ideal as a function of omega, then the corresponding impulse response can be obtained by the inverse DTFT of this. And how do you calculate the inverse DTFT? I will leave this calculation for the class to do, but I would like to put down the important steps here. So, that is done as 1 by 2 pi integral from minus pi to pi H ideal omega e raised to the power j omega n d omega. And in fact, I leave it to the class to compute this for the ideal low pass filter and the ideal high pass filter with a cutoff of pi by 2. I shall just put down the answer for the ideal low pass filter. So, for the ideal low pass filter, this would turn out, for example, to be sin pi by 2 n divided by pi n, wherever n is not 0. So, this is the impulse response H n, and it will be half for n equal to 0. I leave it as an exercise to verify this integral. And I also leave it as an exercise for the class calculate the ideal high pass filter impulse response. I leave it as an exercise. Easy to do once one has a basic introduction to the inverse discrete time Fourier transform from a basic introduction to discrete systems. Anyway, the point was, if we looked at this impulse response, there are three things that forbid one from realizing this filter. Coming back, the first thing was infinite non causality. The disqualifications of the ideal filter. Point number 1, infinite non causality. Now, when is a discrete linear shift invariant system causal? It is causal if the impulse response is 0 for all negative values of the integer index. So, h n is equal to 0 for all negative n is the requirement necessary and sufficient for causality. In this case, or for that matter in the case of any ideal filter, you could take either the high pass or the low pass filter in this case. For both of them, you would notice it is infinitely non causal, meaning that even if I were to delay the impulse response sequence by a few samples, any finite number of samples, you could never make it causal. So, it is infinitely non causal, a serious disqualification, which means that if you wish to realize a causal filter bank, you can't. So, it requires anticipatory behavior if you are doing it in time. You need to use the future to work in the present, a strange situation to be in. Now, non causality by itself is not always a disqualification. It is infinite non causality which creates a problem. Infinite non causality means one cannot make the filter causal by introducing some delay. That is what is a disqualification here. Disqualification number 1. Disqualification number 2. The system is unstable That is, if you look at summation on n mod h n, it is divergent. A terrible thing to happen. Now, this is also indicative of a subtle point. Just because it is a filter does not mean it has to be stable. What it means, the moment you say filter, the moment you say it has a frequency response, what it means is that when you give a sinusoidal input, a bounded input of course, the sinusoidal input, the output is bounded. In fact, the output is a sinusoid of the same frequency. But that is to do with sinusoids. You could very well have some other peculiar input where the output is unbounded. Now, that is troublesome. So, you could have a situation where you get a certain behavior as far as sine waves go, but you are not guaranteed that the output will always remain within bounds for a bounded input. A bounded input may not produce a bounded output. The system is unstable. A discrete time system is stable if its impulse response is absolutely summable. Of course, we are talking about LSI systems here, linear shift invariant systems. So, this linear shift invariant system, whose frequency response corresponds to the ideal low pass filter, whether cutoff pi by 2 or any other cutoff, or for that matter an ideal high pass filter, all such systems are unstable, which can be shown by showing that the impulse response is not absolutely summable. If you try and calculate the absolute sum of the impulse response, it would diverge. Again, I leave this as an exercise for you to show. Take the ideal impulse response of the low pass filter, for example, with a cutoff of pi by 2, and try and show that its absolute sum is divergent. Not very difficult, but an interesting exercise. Disqualification number 2, unstable. Disqualification number 3, a serious one too. The ideal filter is irrational. And what does this mean? Now, let me first explain the meaning of irrational literally. You see, if we say a filter is rational or a linear shift invariant system is rational, if you look at the system function, that means the Z transform of the impulse response, and find that it can be expressed as a ratio of two finite series in Z. So, numerator a finite series in Z, denominator a finite series in Z. If a system function of the LSI system could be expressed as a ratio of two finite series in Z, we say this system is rational. So, of course, when we talk about rational systems, we are automatically talking about linear shift invariant systems. It is only linear shift invariant systems which could be rational or irrational, and rational or irrational refers to systems who have a system function, linear shift invariant systems who have a system function, which means the Z transform of the impulse response exists in some non-null region of convergence. Now, the Z transform of the impulse response of the linear shift invariant system could either be rational, which means it is a ratio of two finite series in Z, or it could be irrational, in which case it is not. Let me give you an example of an irrational system function. The example of an irrational system function could be e raised to the power of z inverse, with mod z greater than 0 as the region of convergence. And of course, the corresponding impulse response can easily be seen to be 1 by n factorial u n, where n factorial is defined by 0 factorial is 1 and n factorial is equal to n times n minus 1 factorial recursively for n greater than equal to 1. Interestingly, this system is stable. So, it is not that all irrational systems are unstable, but irrational systems have a fundamental problem. Irrational systems are unrealizable, at least today. We do not know any neat way of realizing irrational systems. Rational systems can be realized with a finite amount of resource. What do we mean by resource? Adders, multipliers, delays. These are the basic resources of a discrete time realization. A rational system can be realized with finite resource. An irrational system in principle requires an infinite amount of resource to realize. Now, this is all falling in place. The non causality, infinite non causality and instability came as a bit of a surprise, but this third disqualification is not quite a surprise. What we are saying in effect is that if you want an ideal filter, be willing to put in infinite resources to get it. This is the whole I would say actually irony of discrete time system design. I keep mentioning this, whether it is a basic course or an advanced course like this. The irony of many design problems is that you know which ideal you are striving towards, and you also know that you cannot achieve that ideal with finite resources. But what keeps engineers and mathematicians and scientists and what have you active all the time is that you also know that you can go arbitrarily close to the ideal, provided you are willing to invest more and more resources. And there are many ways of doing it. There are different ways of investing resources and going closer to the ideal. Perhaps some paths take you closer to the ideal faster, at least in a certain range of resources, and some paths slower. And again, there are compromises. If you go faster in one sense, you may go slower in the other sense. Nature drives the engineer, scientist and mathematician to no end. Anyway, that was just a philosophical diversion. Coming back to this problem, the ideal 2-band filter bank is unrealizable, but we can go tantalizingly close as we desire. So, you can build a 2-band filter bank arbitrarily close to the ideal if you are willing to invest more and more resources. And over the past 15 to 20 years, people have come out with so many different designs. Now, why have people sought these different designs? Again, that question needs to be answered, but then now we will first answer the easier of the two questions.